Now we'll hear from Aidan McKay. About extending the reach of Gaia DR3 with self-supervision.
Yeah. All right. Hi, everyone. My name is Aidan McKay. I'm a master's student at the University of Victoria in Canada. And yeah, I'll be telling you a bit about my research in building a mass stellar autoencoder. So large sky surveys are already swamping us with data. And this is before even the contributions of future surveys and telescopes like Euclid and LSST. Collaborations such as Gaia and Delve have made billions of stars available in terms of photometry for us to use and do astrophysics with already. My research is in galactic archaeology, and so I'm looking to chemically map both the disk as well as the halo of the Milky Way. And in order to do this, I want to accumulate all the data I have available. And so with this model that I'm going to develop, I also want to make it scalable so that we're prepared for these future surveys. And so the question is, how can we maximize the use of all these data sets for stellar astrophysics? So in order to start answering this question, we need to make a cut somewhere. And I make this cut at Gaia DR3. And so this data set was released last year and made 1.8 billion stars available with photometry and astrometry, limited to 21 in the Gaia G band. And so this is a bit of a limitation, but again, we need to make this cut somewhere. And this still covers 1% of the entire Milky Way, quite a large amount. With these 1.8 billion stars, 220 million of them were made available with this spectrophotometry from the BP and RP instruments. And one thing of note is that this data comes in the form of coefficients that fit a basis function that describe the spectrum. And so these are different than spectra and photometry. They're these coefficients. These are for brighter stars than the full Gaia limit at a magnitude of 17.65 and brighter, but still very useful. Gaia will be the reference catalog, and I will be cross-matching all these surveys onto Gaia for stars at this brightness and above. And so currently my research, as it still is a work in progress, I have curated these data sets to my input. And as you can see, the depth of these data sets reaches quite a bit further than Gaia in some respects. And so this shows us where we can take the model in the future, as well as where we're at right now. One large problem that we're going to have with this data set is that there's a lot of missing values. Just looking at the XP spectra, the XP coefficients themselves, there are 220 million, which is a lot of low-resolution spectra, but out of the Gaia data set, that means that there's still 1.6 billion stars without this information. And so what some people would do, what a common method is to approximate some of these bands as equal to each other, taking the Pan-STARRS G band and the SDSS G band and making them equal. But we don't want to do this, as we may be missing out on some of the differences and inconsistencies in the filters that could unveil differences in the stellar features and the stellar spectra of these stars. And so we need a method to combine all this data and these informative embeddings while still handling the large problem of missing data. So we're looking for a model that will take in all these BPRP coefficients, as well as photometry and multiple bands, and encode them into this embedded dimension. This embedded dimension will be more informative than any of these coefficients or magnitudes by themselves, and will help us do these downstream tasks, such as deriving stellar parameters or deriving distances using Gaia parallaxes. But we don't want to do multitask training on this data set. We want to make this model agnostic to any of these downstream tasks so that we make the embedding and enforce it to be as informative as possible about these stars, to really reconstruct, or to really embed all the usable information in these magnitudes. And so the goals for this model will be to encode the data into a powerful embedding which will natively imputing the information we're missing, as well as extending the depth of these XP coefficients. And so by this I mean, if we were to have the XP coefficients for a star, we'd be able to shrink it down to just the important information, as well as if a star is too dim to have these XP coefficients. We're able to infer that through this encoder and into this embedded dimension. As well, we want to mitigate the selection biases in surveys. And by this, I mean that we want to remove the need to take the intersection of all this data. If we take that, we only end up with a couple of stars that are already really well studied, and we don't learn too much. Instead, I'm able to take the union of all these different surveys together and combine that for this model. And so how do we obtain these embeddings with missing data and without doing supervised learning? That would be self-supervised learning. And so we've already heard a bit about these two different methods of contrastive and masked image modeling at this conference, but just briefly. Contrastive learning, at least in images, takes two different representations of the data. An image is augmented in two different ways and fed through these encoders. And then the contrastive learning will looks to maximize the agreement between these two different representations of the same image while minimizing the disagreements between them. Masked image modeling, on the other hand, requires artificially corrupted data or masked data and reconstructs it using an autoencoder architecture. These algorithms, the MAE and the SimMim, for example, use transformers as the basis for their autoencoders, as well as work a lot better with scaling. The more data that you add to these algorithms, the better it works, and especially when it becomes on the order of millions to billions of data points, which we have in stars. And so this brings us to the algorithm that I've developed, the masked stellar autoencoder, where we pass in sparsely populated photometric data, and it becomes masked where it doesn't exist. This architecture copies more the SimMim and MAE architectures for self-supervised learning, as it's a bit difficult to define how we would augment the data if it's tabular data and these coefficients, as well as the fact that these masked autoencoder algorithms are a lot better for missing data. And so right now I'm training on just a subset of the Gaia data set, those that have these XP coefficients with it, and I'm masking about 50% of them as they're being fed into this algorithm. Currently, the best model works with two separate encoders, each handling one of the modalities of the data, one being the XP and the other being the photometry, and then combining them within this embedded dimension through a couple of fully connected layers. Now, like I said, this is a work in progress, but we have some results to show that are still to be improved with scaling by orders of magnitude. We still have quite a bit to go. But nonetheless, here we have a very large plot of the residuals of the reconstruction of the magnitudes of the coefficients on the top plot, and then the reconstruction of the magnitudes on the right. And so what we're showing here is that even though 50% of the time these XP coefficients are completely masked, we are getting extremely good residuals. On the right, we're showing the plot of when the magnitudes weren't masked, but it is showing that there's no loss of information within this embedded dimension. Here we have some reconstruction plots of magnitudes that don't exist in their surveys. The way that I'm generating these plots and constraining the model then is by synthetically generating these magnitudes using the XP spectra. And so this is done through a tool called Gaia XPy, and on the x-axis of both these plots, we have the photometry generated through the unmasked coefficients, where on the left plot here, we have the photometry generated through reconstructed coefficients only, which are, again, masked 50% of the time. On the right, we just have the reconstructed magnitudes through the algorithm, and like I said, there is some ways to go, but these are very promising results with low scatter. And then here we just have a sample astrophysical task. It's not too pretty yet, I will admit, but training the autoencoder with just only more data, not informing it any more about the spectroscopic labels, not that it's not informed of the spectroscopic labels to begin with, we are obtaining better fits to the data. I'll leave you with my summary, and thank you.
Thank you, Aidan. We have time for questions. Yeah. Benjamin?
Thank you. I didn't quite understand why in this situation a machine learning approach is the best way to go. Coming from galaxies, I have the possibly naive expectation that stellar SEDs are relatively simple compared to galaxies. And so to me that seems like a forward modeling where you have filter curves and SED template library seems straightforward. So why the machine learning approach?
That's a good question. So the machine learning approach is so that we can take all these stars possible. They're only sometimes observed in one survey, for example. But what has been shown before is that these XP coefficients are extremely informative and are able to directly produce things such as the stellar parameters, the ages, and whatnot. And so the original idea came from the fact that we want to take all this photometry and convert it into these pseudo XP coefficients, because there's already been just simple decision trees algorithms that have been used to reduce these coefficients down to all these stellar parameters that we're looking for. And so the machine learning approach is so that we can embed all these different magnitudes and get the information out of them that would be the same information from the XP coefficients, if that makes sense.
Further questions? François?
I don't think you've mentioned what kind of architecture you're using for your encoder.
Yep.
Is it a transformer-based model?
So currently, it is not a transformer-based model. Like I said, we still have a couple orders of magnitude to go with scaling this algorithm, and I suspect that a transformer model will be better when scaling. But currently, it's a residual neural network, a ResNet type architecture, and this could also be why 2 encoders for the different modalities are working better than just one overall encoder.
Okay, good. Thank you.
Other questions online? Not so far. Any questions in New York?
Seems like no. I think we asked too many questions left. Okay, we have a question. Yes.
Hi. I'm wondering about the synthetic magnitude prediction. So are you fine-tuning this to predict the synthetic magnitudes directly, or is this predicting the XP coefficients, which you're putting into Gaia XPY?
So currently, we're training on the loss of the reconstruction of the XP coefficients. And so we're adding, in the next version of the model, constraining the loss by using these synthetic photometry, synthetic magnitudes predicted from these reconstructed XP coefficients. But currently, it's just training on the reconstruction of the coefficients and the reconstruction of the photometry.
Okay, thanks.
So if there are no further questions, let's thank Edin again.